Hello everyone. Continuing from where we left off, we learned about the residue, which is you could think of as like the lowest thing that a number could be congruent to in any modulo system. So let's expand on this idea with the following problem. List all integers between negative 100 and 100 that are congruent to 5 mod n. 5 in this case is going to be the residue. Because according to the previous definition, our R, the residue, must be between 0 and whatever modulo we're working under. And in this case, yes, 5 is less than or equal to 9 and above. Oh, whoa. I messed up those inequalities. Of course not. We can't have that. It's either greater than or equal to 0 or strictly less than 9, or whatever modulo we're working in. And in this case, 5 does fit that criteria. So what this question is really asking us is to find all the integers between negative 100 and 100 where the modulo 9 residue is 5. Now, in order to determine this, we can think of it in terms of the remainder. We want our remainder to be 5. And in terms of the division algorithm, which was A is equal to I'm going to write in this case M times N plus the remainder R. But in our case, we want to find all the values of A that are equal to 9 times some integer n. I should just write 9 times n, keep it consistent, plus the residue, which we know is 5, where n is between negative 100 and positive 100. No, I'm not sorry, not my n, my A. So I've been making videos all day and I am a bit starting to burn out a little bit. So, all right, let's think. Let's think. Well, we can think of, all right, what's the least possible integer that has a residue of 5? Well, we need to think in terms of multiples of 9. So, for instance, I know that like 9 times 12 is 108. So if I'm starting at negative, I would want to check, all right, negative, let's say n is negative 12. That would get me that 9 times negative 12 is 108. Well, I also want to add 5 to that because it has to fit the residue system. So in this case, the negative 108 plus 5 turns into negative 103. But this negative 103 is less than negative 100. So we actually cannot use this because our value for A is just too low. Negative 103 is less than negative 100. But it gives us a nice idea on where to start because now I can say, all right, what if n is the same as negative 11? Well, then we do 9 times negative 11 plus 5 is the same as, well, negative 99 plus 5, which is negative 94. So that definitely fits the criteria. And now we can just keep going up with values of n, where n is an integer, until we get an answer that's over 100, or that we know will be over 100. So n, next one would be equal to negative 10. And 9 times negative 10 plus 5 is equal to negative 85. So next one up is negative 9. 9 times negative 9 plus 5, well, that's negative 81. Plus 5 is negative 76. N is equal to negative 8. 9 times negative 8 plus 5 is equal to, well, that's negative 72 plus 5, which is negative 67. And we'll just keep going. Negative 7. 9 times negative 7 plus 5. That would be negative 63 plus 5, negative 58. N equals negative 6. 9 times negative 6 plus 5, which is negative 54 plus 5 is negative 49. N is equal to negative 5. 9 times negative 5 plus 5, that would be negative 40. N is negative 4. So 9 times negative 4 plus 5 is equal to negative 31. N is equal to negative 3. So 9 times negative 3 plus 5 is equal to negative 22. N equals negative 2. 9 times negative 2 plus 5. Well, plus 5, that's a negative 13. N equals negative 1. 9 times negative 1 plus 5 is negative 4. Oof. Okay, continuing on. Alright. Now we got 0. N equals 0. So 9 times 0 plus 5 is equal to 5. And we probably see a pattern forming in our results. We're just adding 9 each time. So if you were doing this on your own, you probably could have figured out the rest of the values pretty logically, but I don't like to take those shortcuts, so we're just going to list them all out. N equals 1. 9 times 1 plus 5 is 14. N is 2. So 9 times 2 plus 5 is 23. Then we have N is 3. So 9 times 3 plus 5 is 32. N is equal to 4. So 9 times 4 plus 5 is 41. N is equal to 5. 9 times 5 plus 5 is equal to 50. Ooh, my hand. Alright. 9 equals 6. So 9 times 6 plus 5 gives us 59. N is equal to 7. So 9 times 7 plus 5 is the same as 68. And is equal to 8. So 9 times 8 plus 5 is equal to 77. And is equal to 9. So 9 times 9 plus 5 is equal to 86. Oh my gosh. Alright. Now we're getting close. So, n is equal to 10. Which means 9 times 10 plus 5 is 95. And we have a feeling the next one's not going to work, but let's just check it out. N is 11. 9 times 11 plus 5 gives us 104, which is too much. It's too great of a number. It's past 100. So, cannot include that. And that is it. All the integers that are congruent to 5 mod 9 are listed right there. Because we made sure that each of them had that remainder of 5, or that residue of 5. So, what this establishes is, let's see, just the most fascinating thing, that all of those values we just discovered, I'll write them in blue, are congruent to each other under modulo 9. So negative 94 is the same as negative 85, is the same as negative 76, is the same as dot 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 dot. We'll just continue on and on and on. As the same as 86, which is the same as 95, which is the same as 3 mod. Oh, wait. No. Which is the same as 5 mod 9. So, there we have it. There we have it. All these values, and these are just a limited set. This is a limited set between negative 100 and positive 100. They are all congruent. They are all congruent to 5 mod 9, and where 5 is our residue. The I can't say least anymore because now we have negatives in there, but sort of the lowest positive value. Now, what all this is an example of what is called a residue class, sometimes called a congruence class or an equivalence class. So all those values are congruent to 5 mod 9, and they make up a single modulo 9 residue class. So we could typically, in higher level math classes, we would write it as something like negative, it goes on, but if we want to limit it to between negative 100 and positive 100, we could write it out like a set, where the set of these values dot dot dot, not really dot dot dot, but we get it, to 86 to 95, these all make up, this set is a residue class. And even looking back to some of the previous work we had done, let's see. We have these other residue classes already discovered. So, for instance, here is the residue class under modulo 7. It's the residue 5 modulo class under mod 7. And here we have the modulo 7 residue class of 1. So we've already discovered these equivalence, congruence classes, residue classes in the past. It's just now we are defining them as a special type of structure.